Okay, so if you look at June 2022 P23, question 5B part 3, so the start of the question is actually from B here. You have a laser that emits a beam of electromagnetic waves of frequency 3.7 times 10 power 5 15 Hertz in a vacuum. Then after that, there were some questions there that we were supposed to have done, but I already discussed it previously. So part 1, they ask you to show that the wavelength of the waves is actually 8.1 times 10 power minus 8 meter. This one is just a showing question. And after that, state the region of the electromagnetic spectrum in which these waves belong. So that time I reproduced back the electromagnetic wave spectrum and we found out that this one is actually ultraviolet. Okay. Yeah. So wait, another student just joining. Yeah. Hi, Regan. We are in June 2022 P23, question 5B3. All right. Yep. Hi. So we just started a little only. I haven't really started anything much. Now, if you look at part 3, the beam from the laser now passes through a diffraction grating of 2,400 lines per millimeter. A detector sensitive to the waves emitted by the laser is moved through an angle or arc of 180 degrees in order to detect the maximum produced by the waves passing through the grating as shown in figure 5.2. All right. So here, what we have is a laser beam that is being shot through a diffraction grating. And then after that, there is a detector right behind it that will move along this arc that is 180 degrees. So if this is your laser beam and you shoot it through your diffraction grating, you know that once it passes through your diffraction grating, it will split into a number of beams. So the first beam will be the one right at the center, and then after that it will split into another few more. This one is number 1, number 2, number 3. So this one, we will call this, the one at the center is first order. Sorry, the one at the center is 0 order. Then the next one is first order, second order, and third order. So on the other side of the center beam, it will be symmetrical too. So you expect to see another set of beams, the same number also. So this one would be n equals to 1, n equals to 2, and n equals to 3. All right, so this is what's happening right now. So the maxima that they're talking to you about right over here is actually you detecting the image once it hits the detector. Basically, you're trying to find the point where you have constructive interference. All right. So if you look at the next page is asking you to find the number of maxima detected as the detector moves 180 degrees along the line shown in the figure previously. Show your working. Okay. So be careful with the wordings that they use here. They are not asking you to find the maximum order number. They are asking you to find the number of maxima detected. The total number of maxima detected. In other words, that's what they want. They want the total number of maxima that can be detected with this current arrangement right now. So to do this question, I'll have to write the workings on the left-hand side. Now, this is a diffraction grating. So we know that for diffraction grating, there's always one specific equation that we'll use. That one is d sine theta equals to n lambda. So since we are interested in finding out the total number of maxima, we must first find out what is the maximum order number in the first place. So in our case, we can say n is max when theta is 90 degrees. So you replace these values inside your original equation. D sine 90 equals to n max lambda. So n max would actually be d over lambda, because we already know in the first place sine 90 is equivalent to 1. Okay, so you just do this, you're going to get the n max. So the n max is the ratio of d over lambda, but before we can go through that, you need to look at whether do you have the value of D stated inside the question or not. You see, the question just merely mentioned to you 2,400 lines per millimeter. This is actually N, the number of lines per unit length. So previously, I mentioned to you before, the relation between D, which is the distance between the slits, and number of lines per unit length was this. D is equals to 1 over N, okay? So if you already have the N value, D would just be 1 divided by 2,400. But the units of this D now will actually be millimeter, because this one is 2,400 lines per millimeter. When you take 1 over N, you are actually taking 1 millimeter divided by 2,400 lines. So that's why your unit here would be in millimeter. So you want to change it back to meter, you need to multiply with 10 power minus 3. So you're going to get this. Okay. To change from millimeter to meter, you really just need to multiply with 10 power minus 3. That's why you're getting this value right here. That's why you're getting this value right here. So now you sub in the values, you will get this 10 power minus 3 over 2,400 divided by lambda. Lambda is already given in the previous part of the question. They already told you that the laser was don't know this frequency, but then after that, they subsequently asked you to show that the wavelength was this value. So the value of the wavelength is already something that you know, which is 8.1 times 10 power minus 8. So you go and take the value 10 power minus 3 divided by 2,400 divided by 8.1 divided by 10 power minus 8. You will get the value as 5.14. Okay, so this one is the maximum possible order number that you could get. From here, what do you want to do? To get the maximum order number, you just take the integer values only. Or in some cases, people will just tell you, just round down the value. All right, it will mean the same thing. All right, for some people, they will just tell you take the integer values only. And then for some people, they will just tell you just round down. Okay, if say, for example, your N max that you get is 6.85. In maths, we know that this one by right should be rounded out to 7, right? But when it comes to finding the maximum order number for diffraction grating, do not ever round up. Even if you were to get 6.85, you are supposed to always round it down. So this one should be 6 only, okay? Or looking at another way, just take the integer value. All right, so back to this question, your N max is 5.14. You're supposed to take the integer value only, so it should be 5. Okay, this is the maximum order number. But the question wants the total number of maxima. So you have one step left in your working. To find the total number of maxima, you will have to take 2 times of your N max plus 1. Okay, so this one will be 2 times 5 plus 1, giving you 11. All right, so this is the total number of your maxima. Now, why is it specifically we need to plus 1 is because the plus 1 is supposed to include the maxima right at the center. When you are finding the N max, you are finding only for one side. You see, from here to here, it will go from 1 to a max value. So in my case, for the question, it was going from 1 to 5. All right. But then after that, why is there a 2 in the first place? It's because there's a same repeating pattern on the other side of the center line. So this one will also be going from 1 to a max value. So if we want to take into account the maximum on both sides, I need to take N max times 2. And then I also need to plus 1 because I need to take into account the maxima right at the center. Okay, so this is why I need to have 2n max plus 1, giving me an answer of 11. So let's check the answer. Yes, your number of maxima is, strictly speaking, just 11. All right. Okay, then if you're okay with that, then let me just move on to the last part. Okay, so I'll just clear off everything here. Now, for your case, they mentioned that the laser is now replaced for one that emits electromagnetic waves with a wavelength of 300 nanometer. Explain without calculation what happens to the number of maxima that is now detected. Assume that the detector is also sensitive to the wavelength of the electromagnetic waves. Okay, so for this one, I think it's better if I just show back the original workings that I have. Right now, they just replace your wave with another different wave that has a value of 300 nanometer. They want you to find out what happens to the number of maxima that you can detect now if you were to repeat the same detection over 180 degrees. Okay, so 300 nanometer is the new wavelength of the wave. If you refer back to the previous wavelength for the previous laser that you used, the wavelength of the previous laser was actually 8.1 times 10 power minus 8 meter. You change it to nanometer, it will be 8.1 times 10 power minus 8 divided by 10 power minus 9 to change it to nanometer. It will actually be a very small value in terms of nanometer. It's actually 81 nanometer. Wait, let me just double check the answer. Yeah, it's just 81 nanometer. Okay. This is the old wavelength that you use. It's 81 nanometer. This one is actually not visible light. Okay, this one was actually ultraviolet. We've already answered a question subsequent to that asks us to identify what is the wave that has this particular wavelength. This is actually ultraviolet. It's 81 nanometer. So the new wave that we have is having a wavelength of 300 nanometer. So clearly this one is bigger than this. It's bigger than the old value. All right. So to find out how does it relate to your number of maxima, recall that just now we already derived how to find the maximum order number. Maximum order number is actually the ratio of your slit separation divided by your wavelength. Okay. So in our case here, when we did this experiment, we only replace the laser with another different wavelength. Everything else remains the same. The apparatus, everything else remains the same, including the diffraction grating. So this D here, the slit separation ought to remain the same as before. Okay. So if we want to word the answer, we can say something like this. N max is equals to D over lambda. So D is constant. Therefore, N max is inversely proportional to wavelength. Okay, so in my case, I can say that N max is inversely proportional to my wavelength. Okay, so from there, I can say that the wavelength is larger now when I change it to a new wavelength. The wavelength is larger, therefore, max order number decreases. Okay, so if my max order number decreases, how would this then affect my number of maxima? Just now, we also know that total number of maxima is actually 2n max plus 1, isn't it? So if it's 2n max plus 1, the plus 1 here obviously is a value that is fixed. There's nothing we can do about it. It will always be there. Now this n max here has changed. It has reduced. So if total number of maxima is 2n max plus 1, the plus 1 here being fixed, but the n max itself drop, it follows that my total number of maxima must drop. Okay, so here I can just say this one plus total number of maxima decreases. All right. Now you look at what the marking scheme wrote. I think they wrote it in a very simple manner. They just say wavelength increase, so number of maxima decreases, but they didn't really tell you why. How do they get that conclusion? All right. So the conclusion is all based on what I just wrote here. Okay, so if this one is okay, then I move on to the next question. The next question ought to be a circuit question. So this one is specifically on IV graphs. Okay, now if you look at part 6, or rather question 6, on the figure here, sketch the IV characteristics of a filament lamp. Okay, so this one is specifically asking you about a filament lamp, and you're supposed to sketch an IV graph out of it. So there are a few things that you should have learned from your current electricity, specifically when it concerns filament lamp. So for filament lamp, the first thing you would have learned was that the resistance increases with PD. Or sometimes they can also say it increases with current. It's the same thing. It's interchangeable. The gist is that you need to understand that filament lamp resistance tends to increase. So in our case, let's just say it increases with PD. Then after that, for an IV graph, the IV graph will be able to tell us the resistance changes depending on how it's drawn. So that time specifically I mentioned to you, if you were to try to take gradient, not the gradient of the tangent, but rather the gradient from origin, that would allow you to find out what is your resistance at that particular point. So gradient from origin over here is I over V is actually the inverse of your resistance. Since resistance in the first place is ratio of V over I. So I over V is going to be 1 over R. Okay. So from here, just now I mentioned that your resistance should be increasing with PD, isn't it? So in our case, we already know that the gradient from origin is inversely proportional to R because of these two things here. Gradient from origin is actually inversely proportional to R. If our resistance were to increase, because it's a filament lamp, the gradient ought to decrease. Okay, so in terms of the IV characteristics for the filament lamp that we need to sketch a graph whose gradient from origin is decreasing with PD. So it will be something that looks like this. Like this. And then like this. Sorry, let me just redraw this properly. This one is the correct one. Maybe I should just draw it in one shot. It looks like this. Okay, this is as best as I can draw it. Now, this graph is showing you that gradient from origin is decreasing. So what I mean by that is that if you just take 2 points on the graph, let's say on the right-hand quadrant, this one and this one, for the first point here, the gradient from origin is given by this line. For the second point, the gradient from the origin is given by this line. You can see that the gradient is actually decreasing. Okay, so this one would tell me the resistance is actually decreasing right over here. Okay, so this is the graph shape that you should have. And you should also have the shape on this quadrant here too. Okay, you don't just draw your graph on this quadrant, you also should draw your graph on this quadrant too. Okay, now the reason is because of this. You have to take into account that your filament lamp can also have current or PD in the opposite direction. So what do I mean by that is this. You have, say, a circuit with filament lamp like this. Okay. In this particular arrangement, current flows like this in this manner. Your current flow is going like this, all right? And then you have positive and negative terminal here. This one is representing what you're seeing right over here. Okay, when you measure the voltage and current, they are of a specific direction. The variation is given by this. Okay, you have positive voltage, you have positive current. Now for the other part here, where you start to have negative voltage and negative current, it's really just you switching the polarity of your battery. So what do I mean by that is something like this. So if you go and switch battery polarity, if you go and switch the battery polarity, you're going to get something like this instead. This is your same filament lamp, and then this is your circuit. Now, because you switch your battery polarity already, this is now positive, this is now negative. Current will actually now flow like this. Okay. So notice that your current direction flow is actually in the opposite direction. Okay, this is where you get your negative current and negative voltage from. All right. So in your current case, your filament lamp is still working. All right. It still has some value of resistance there. It still is emitting some light, but you need to take into account that the voltage and currents is actually in the opposite direction. That's why you have this pink colored line here that I highlighted. All right. Sorry, that's why you have this line here that I highlighted in pink. All right. So let's just check the marking scheme, see what they say. They just say line passing through O and is in the first and third quadrants only. And the gradient of line becomes less steep in both quadrants and are roughly symmetrical. All right. So that makes sense. This is what we draw. Is following exactly what the marking scheme wanted. Now, for second part, explain the shape of the line that you just drew in A1. Okay. So explain the shape of the line that you just drew in A1. Let me have a look at what the answer said. Oh yeah, explain why the resistance decreases. Okay, so they're basically asking you, why does the graph become a curve? All right, so why does the graph become a curve in the first place? We know the graph curves because the resistance changes, but specifically, why does the resistance change in the first place? So we need to explain why the resistance changes. So one thing we can do is you can write something like this. As current increases or voltage increases, the temperature of the filament lamp increases. Okay, when current increases, the temperature of the filament lamp increases. This causes resistance of the filament lamp to increase. Okay, so when the temperature of filament lamp increase, your molecules or atoms inside your filament lamp are actually vibrating faster. So it's actually preventing more resistance to the flow of electrons, or rather to the flow of current. That's why your resistance will increase. Okay, so as current increase, temperature of filament lamp increase. This causes resistance of the filament lamp to increase. And then after that, since R is the ratio of V over I, thus the graph curves. Okay, right. So let's just see what the marking scheme wrote. Yeah, they say as current increase, temperature of the filament lamp increase or filament wire. And then after that, as your current temperature or voltage increase, the resistance of the wire or lamp increases. And then after that, subsequently, the graph will curve because the ratio changes. Okay. Here they will specify the ratio of V and I increases, ratio of IV decreases. Okay, let's just write this inside. Since R is equals to VI, wait, now let me just write this. I will rewrite this answer here. Just give me a moment. I over V is equals to 1 over R. It was actually equals to your gradient from origin. So if my resistance is increasing, my ratio I over V decreases. Okay. So in turn, this causes the graph to curve downwards. Okay. So in your case, resistance is already established to increase. You can say something like this now. The ratio of I over V decreases because resistance increase, the ratio of I over V must decrease. Ratio of I over V decreases, thus graph curves. Okay, you can just write the graph curves, right? That's the graph curves. This will explain the shape of the graph that you're seeing. Okay, so first point is just saying that temperature of the filament lamp increase. Second point is you saying the resistance of the filament lamp increases. The last point is you saying ratio of I over V decreases. That's your third point. Okay, so this is 1 point and this is 1 point. All right. Okay, now if you move on to part B, a conducting wire has a length of 5.8 meter and a cross-sectional area of 3.4 times 10 power minus 8 meters squared. The resistivity of the metal wire is 5.6 times 10 power minus 8 ohm meter. Calculate the resistance of the wire itself. Okay. So whenever you see mention of length and resistivity, you already know what equation you want to use. This one is always going to be R equals to rho L over A. Okay. So they want the resistance of the wire, which is R here. You already know all the other values. So you just need to sub in the values. In my case, it would be R equals to 5.6 times 10 power minus 8 times with the length of 5.8 divided by cross-sectional area of 3.4 times 10 power minus 8. Okay, so from here, your R will be 5.6 times 10 power minus 8 times 5.8 divided by 3.4 divided by 10 power minus 8. You will get the answer is 9.55 ohms. All right. So again, let's check with the answer. Yes, round it up to 2SF, it will be 9.6 ohm. Okay. So that's for this particular question. Then I move on to the next one. So I'll clear off the screen here. For the last part, if you look at C, you have a resistor of resistance R that is placed in the circuit with a cell of negligible internal resistance, two switches S1 and S2, a second resistor of resistance to R, and three ammeters X, Y, Z. The circuit is as shown in figure below. The reading on ammeter X is 1 amps when S1 is open and S2 is closed. Complete the table 6.1. So if you look at the first row itself, where both switches are open, if you look at this diagram here, you see that there's no closed circuit anywhere. There's no possibility of any current flowing at all. There's no current flowing through here, through here, through here, nor through here. That's the reason why your current readings in all three ammeters are considered to be 0. Now, if you then look at the first row, where they say S1 is open, S2 is closed, let's consider this case here. S1 open, S2 is closed. So there's an open circuit at the top part of this parallel connection here because the switch was open here. So this part is considered to be an open circuit. Therefore, no current. Okay. So along this path here, you have ammeter Y. The current reading on ammeter Y ought to be 0. Because as mentioned before, this path here has no current flow. For the part where current is flowing, current will flow out from the battery here before reaching this junction. But because the top part is an open circuit, no current will actually flow through. All the current will instead flow through the bottom path before returning to your battery. Okay, so we had ammeter X here, whose current is already stated to be 1.0 amps. And then as the current continues flowing from battery to the junction, all the current continues flowing down the path for your parallel connection. When you had ammeter Z here, because the current never split up in the first place, its current will be the same as before the junction. In other words, the current will be the same as current through ammeter Z. Sorry, current through ammeter X. So here, if before this, the current was 1.0 amp, right now we're also going to have 1.0 amp here. Okay, so if we fill out the table now, reading on ammeter Y is 0, reading on ammeter Z is 1.0. Okay, so this is for this one. Now, for the third row, where we're talking about S1 being closed but S2 being open, let's consider another different situation where S2 is closed. Let me just rewrite this. S2 is closed, but S1 is open. Okay, so in our case, there's actually some sort of breakage at the bottom part of our parallel connection. This part is open circuit. Therefore, no current. Okay, so current will not flow through this path at all. Okay, but again, we know that there's an ammeter right over here, ammeter Z. The current through ammeter Z would actually be 0. Okay, so if you then consider how current is flowing through the remainder of your circuit, it comes up from your battery, it reaches this junction, but because it cannot flow through the bottom path, all of it will just flow through the top path of your parallel connection before going back to your battery. Okay, so what we're interested to know now is what is the current through ammeter X and what is the current through ammeter Y here. Okay, now to be able to find out what is the current now, it will be easier to see if we were to simplify both these circuits that we've drawn. So for the first diagram that we have, we can actually simplify it to become something like this, where you only have a single cell and a single resistor. whose resistance is 2R. Okay. And then after that, for the second diagram, we do the same thing where we again draw a simplified circuit that consists of a single cell and a single resistor. But this time our resistance is just R. Okay. Now, for both these simplified circuits here, we know that a current flows through your circuit now without splitting. Now, what is the current that's flowing through this simplified circuit here? The current that's flowing through this simplified circuit here is actually the current through X, okay? Because right now the current here is actually representing the total current through the circuit. When you're talking about the total current through the circuit, it ought to have been measured by ammeter X, because you can see from the diagram before they were being simplified, ammeter X is actually measuring the total current through circuit before they even split out at the parallel connection. Okay, so in our case now, we have 1 amp flowing right over here. Okay, now before we can even work out what is the current for the second diagram, there's one thing that we need to realize first. The EMF value for both circuits are actually the same because the cell wasn't removed or replaced. The only thing that we did here was just to switch on and off switches S and 1 separately. Okay, so the EMF value for both circuits here remain the same. That will mean that the PD across each of these resistors here would actually be the same. Now, what do I mean by that is that if let's say I were to give you some values for your EMF, if this one was 6 volts here, the PD across your resistor will be 6 volts too. Similarly, this one, if the EMF across your the EMF across the cell is 6 volts, the PD across this resistor here will be 6 volts too. Okay, this is in accordance to Kirchhoff's second law. So what can you now do from here? If you apply V equals to IR, and you apply it to this, let me just circle it properly for you, sorry. If you apply it to the resistors here, as well as the resistors here, you could actually say that V is constant, therefore current is inversely proportional to R. Okay, now from here you can start to make out some sort of relation. If I'm going from the first diagram to the second diagram, how did my resistance change? I actually went from 2R to R. Okay, so my resistance has actually decreased by 2 times. Therefore, my current should increase by 2 times. Okay, because there's an inverse relation here. So my current here being 1 amp, that would mean that my current through my second circuit would actually be double. It will be 2 amps. Okay, now this current 2 amps is actually the total current flowing through the circuit, which is the current that's actually measured by my ammeter X. So the current through my ammeter X is actually 2 amps. Okay, so we already established that that current, as it flows through and reaches the junction here, it did not split up because the bottom path had an open circuit. No current is actually going to flow through there. Instead, all the current is going to flow through the top path of your parallel connection. So ammeter Y is going to get all the current, which is the same as the current through ammeter X. It will be 2 amps also. So right now we're going to get reading on X as 2.0, reading on Y is 2.0, and reading on Z is going to be 0. Okay, just to illustrate again how current is flowing through your second circuit, it just flows like this. Okay, so that's for this part. And now for the last row, where both switches are closed, how will we do this? So let's consider a case where, let me just rewrite this, sorry. Let's consider a case where both S1 and S2 are closed. So when both S1 and S2 are closed, you consider how the current flows out from the battery. It comes out like this. It reaches the junction, it will now split up, okay, because there's no open circuit here. So current will actually split up at the junction, giving you IY here and IZ here. Why IY and IZ is because you have ammeter Y here and ammeter Z here, okay? So that current will actually split out at this junction before combining back here and flowing back to the battery, okay? Now, for the part where you have ammeter X here, let's call the current through it as IX, okay? We will make use of these current values later on, okay? But first, what we're interested to know is how are we going to approach this question? Now, because you have a parallel connection here, the first thing you would tend to do is to simplify that parallel connection there. If I want to find out the resistance in parallel here, it will be 1 over R plus 1 over 2R power negative 1, giving me 2 over 3R. So right here, I have a equivalent resistance of 2 over 3R, okay? Now, from here, you can again see that there's a total current flowing through your circuit like this. This one will be the current through ammeter X again, okay? Now, I want to find out what is this current. The best way to go about this is to make a comparison with one of the earlier circuits that I've done. In our case, you notice that this is a resistance of 2 over 3R. If you want to compare with one of the earlier circuits, it will be easier if you compare with the one where you had 2R, meaning to say you compare with the first circuit. Now, if you recall what we did in the first circuit, we actually simplify it. So when we simplify it, we got a diagram that looks like this. And then from there, we also already established that the current that was flowing through that simplified circuit was just going to be 1 amp, okay? So now we want to make a comparison between this diagram and this diagram, okay? We again apply V equals to IR here, but this one is again applied to your resistor here and also to your resistor here, okay? Now, as mentioned earlier before, your EMF for both circuits should be the same because you did not actually change out the cell. So that time I mentioned to you, if you had a EMF value of 6 volts here, your PD here would be 6 volts. Similarly, if your EMF here is 6 volts, your PD here again would be 6 volts. Okay, so here you can again draw back that same conclusion as before, where we say that V is constant. Therefore, I is inversely proportional to R. Okay, now from here, you now start to make a comparison between the two diagrams. Going from this first diagram to the second diagram, like this, what actually happened to the resistance? We can already see that our resistance here was originally 2R. But then after that, when we went to the second diagram here, it was 2R over 3. Let me just rewrite this resistance value. 2 over 3R is actually the same as 2R divided by 3. So going from the first diagram to the second diagram, our resistance value actually decreased by 3 times. Therefore, our current must increase by 3 times. So if my current here is 1 amp, in the new diagram here, my current must have increased by 3 times. So from 1 amps, it will become 3 amps. So these 3 amps would be the current through my ammeter X. So this one will be 3 amps. Okay, so that's for one part of your circuit right now. but we're still left with IY and IZ. Okay, so how are we going to find out what is IY and IZ in the first place? For this particular case, we need to make use of Kirchhoff's first law. Okay, now if you recall from Kirchhoff's first law, sum occurring into a junction is equals to sum occurring out of a junction. Our junction here being this part here. So I can say that IX is equals to IY plus IZ. Okay, so there's one part here, one relation here that I can get. Now, if you were to again apply V is equals to IR, let me just get something right here. Okay, if I again apply V is equals to IR for these two resistors here, V is again constant, therefore I is inversely proportional to R. There was a relation that we originally had. From this relation here, I is inversely proportional to R. You can actually get one ratio out of this. Just let me rewrite this properly. If I is inversely proportional to R, this will tell me that the ratio of current IY to IZ is actually 1 over RY over 1 over RZ, which in turn becomes RZ over RY. So from here, what is the ratio of the currents then? IY over IZ is actually going to be 2R over R, which in turn gives me IY being 2 times of IZ. This is relation number 2, sorry, not number 1. This is relation number 2 that you can get. So this is relation number 2. Now, if you sub in relation number 1 to relation number 2, you ought to be able to get out one of the currents. So let's sub in the values. So if I say sub 2 into 1, subbing 2 into 1, you will get 3.0 for IX, 2IZ plus IZ itself. Okay, IX we already know is 3.0 amps. Okay, then after that, IY is actually equals to 2IZ, which we already established just now. Okay, so your resulting expression will be what you see on the screen here. So IZ eventually will become 1.0 amps. Okay, so this is one answer here. And then if you wanted to find out what is IY, it is very straightforward now. What you just need to do is to say something like this. Let me find a different color to use. Okay, your working will be continued over here. From equation number 1, your IX was 3.0. Your IY is what you want to find right now. After having found IZ as 1.0, IY is therefore 2.0 amps. Okay, so now you have the complete values for all the ammeters. For IX, you have 3.0. For IY, you have 2.0. And then for IZ, you actually have 1.0. Okay, so let's check our answer and see whether what we've done here is correct. So second row is 101. Third row is 220. And then the last row is 321. So let's see whether we got it right. It's 321. Okay, so what we've done here is correct. Let's move on to the last question then. Now for the last questions, question 7, fluorine 18 is an isotope that decays to an isotope of oxygen by emission of a beta plus particle. Complete the nuclear equation for the decay, including all the particles involved. So here, one of the first things that we know here is that your fluorine will change to an oxygen. and then there's a beta plus particle here. So if we write out the nuclear equation, we are going to get something like this, where we get oxygen plus your beta plus particle plus your electron neutrino. Okay, now you should note that when you have beta plus particle, it comes from your beta plus decay. So beta plus is actually your anti-electron or your positron. It starts with P. So as I mentioned previously, if it starts with P, then it must be proton, changing to neutron, giving you your beta plus and your electron neutrino. So let's fill in the proton number and neutron number here first. You will get 1, 1, 0, 1, plus 1, 0, and 0, 0 here. Okay, so this pair of particles, your beta plus and your electron neutrino will always come together. Okay, these are your lepton pairs. Okay, your positron being this one, or your beta plus, and then this one being your electron neutrino. Okay, so that's the reason why you actually had these two pairs here, your beta plus and your electron neutrino. But let's just fill in your proton number and neutron number for this equation too. So because it's beta plus, you have plus 1, 0 here. And then because this is your electron neutrino, this will be 0, 0. Okay. Now, what about for the oxygen atom? Now, for your oxygen atom, there's one thing that you would have known before this. Proton number and neutron number is always conserved in a nuclear reaction. Okay, when it comes to your proton number and nucleon number, they will always be conserved. Let me just rewrite the wordings properly for you. It will always be conserved in a nuclear reaction. Okay, so what this means is this: the proton number before and after reaction remains the same. Okay, proton number before and after reaction remains the same. You could also replace this with nucleon number before and after reaction remains the same. Okay, so we're applying it for our nuclear equation here. If you look at the proton number itself, if you apply conservation of proton number here, we already have 9 before the reaction. So after the reaction, we must also have 9. So here we already have 0, and then we already have 1. So what should be the value right over here in order for us to get back 9? So simple calculation will tell you it's actually going to be 8. Okay, we need to have 8 here, so that plus 1 becomes 9. Okay, then you then look at your nucleon number. Your nucleon number is 18 before the reaction. After your reaction, you notice you have 0 here, you have 0 here. What should be the value here so that you get back 18? So here, you can already guess it should be 18. Okay, so this is our nuclear reaction here, the equation that represents it. But let's just check our answer first. So you have oxygen 18.8, and then beta plus 0, 1, and then electron neutrino 0, 0. Okay, so that's for this. Now, then if you look at part 2, a quark in fluorine-18 nucleus changes flavor during the decay. State the change of this change of flavor. What was actually the thing that has changed here? What flavor or quark has actually changed here? So because you are having a beta plus particle during the nuclear decay, beta plus decay is involved here. So we already work out the beta plus decay equation right over here. If you're talking about proton changing to neutron, what we know is that you actually have up, up, down for the proton, and then up, down, down for the neutron. What has actually changed here is that you will see that one of your up quarks has actually changed to a down quark. So your answer here would actually be up quark to down quark. Okay, so that is for part 2. Now, if you look at for B is saying that a hadron has a charge of -2e, where E is your elementary charge. State and explain whether the hadron is a meson or a baryon. Okay, so there are two terms here that we need to know first. What is meson? What is baryon? So let's go through some of the terms that we need to know. Now, in the first place, you will have learned what is a hadron. A hadron is just a group of quarks. That is what a hadron is. Then when it comes to what is a meson is actually a pair of quark and antiquark. Okay, a pair here would mean that you have two quarks here. Okay, specifically one must be a quark and then the other must be an antiquark. All right, and then the last one that you will need to know is what we call a baryon. Now a baryon is just a group of 3 quarks. Okay, you can think of it as this. Hadron is a more general definition for a group of quarks, whereas meson and baryon are more specific definitions for group of quarks. Okay, so let me rewrite this. They're actually more specific classifications for group of quarks because they will tell you how many numbers of quarks are required and whether they should be quarks or antiquarks. Okay, so now what the question mentioned is that you have a hadron, which is a group of quarks, and they carry a charge of -2e. State and explain whether this hadron itself is supposed to be a meson or baryon. Okay, now before we can even go further from here, there's also the need to know what are possible quark charges. Now, when it comes to quark charges, you have +2/3e, and this belongs to up, charm, and top quarks. And then after that, you also have -1/3e. And this belongs to down, strange, and bottom. These are all quarks. Okay. Now, just as we have quarks, we also have anti-quarks. All right. Anti-quarks have opposite charges. Okay. But magnitude remains the same. Okay. Magnitude remains the same. Okay. So if we have up, charm, and top quarks carrying a charge of +2/3e, their antiquark equivalents will be -2/3e. And then similarly, if we are talking about down, strange, and bottom quarks having a charge of -1/3e, their antiquarks equivalents would have +1/3e. Okay, so we actually have 4 different possible charges to consider here. The question stated that the hadron must carry a charge of -2e. This means that when your quarks are all combined together, they must give you a resultant charge of -2e. Now, when you consider that quarks normally only have fractional charges, a resultant charge of negative 2e is actually quite large. So to get a large negative charge here, it kind of implies to you, you need to use the largest possible negative fractional charges here, so that when they add up, you're going to get a resulting large negative charge. So let's just consider what are the possible fractional charges that we have. We actually have plus 2 over 3e minus 2 over 3e plus 1 over 3e and then minus 1 over 3e. Now, minus 2 over 3e and plus 2 over 3e, these are actually from your anti-quarks. Okay, so what is the largest possible negative fractional charge that we have? That one will actually be negative 2 over 3e. Now, here, if we were to do some addition to these fractional charges here, you will see that negative 2 over 3e plus with negative 2 over 3e plus with negative 2 over 3e again gives you negative 2e. Okay, you need to add negative 2 over 3e 3 times to get a resultant charge of negative 2e. Okay, now just now it was already mentioned to you that meson consists of a pair of quarks and antiquarks. This one means that you need to have 2 quarks to form a meson. And then we also mentioned that baryon must have 3 quarks, isn't it? So right now, if we needed to add negative 2 over 3e 3 times, this means that we need 3 quarks. It therefore must be a baryon right now. Okay, so how do we word our answer? You can write it in this manner. Taking the largest possible negative fractional charge of negative 2 over 3e and adding them together 3 times gives negative 2e. Okay, so therefore there are 3 quarks, so it must be a baryon. Okay, so that's how you would actually word your answer. Okay, the marking scheme actually gave some very vague wordings to your answer. They just mentioned this must be 3 antiquarks as the largest negative quark charge is negative 2 over 3e. Mesons can only have a charge of 0 and plus 1e. So hadron is a baryon. Okay, it's pretty vague, isn't it? So it would be better if you were to write your answers like this. At least this makes much more sense for you. Okay. Now, then from there, we move on to the last part, which asks us still a possible quark composition for the hadron. Okay, now for a possible quark composition for the hadron, we already established that this one is a baryon. So you must have 3 quarks added together that gave you your negative 2e. And the quark must be negative 2 over 3e. So when it comes to negative 2 over 3e, a charge of negative 2 over 3e, you actually have anti-up quark, anti-charm quark, and then anti-hot quark. Okay, so you can choose any from these 3 quarks as your combination, or you can actually just choose one of them alone. Okay, any combination would do. So in my case, let's just say I give you 2 variations of the answer, where maybe I just choose anti-up quark. So in my case, I would just say it's anti-up quark, anti-up quark, and then anti-up quark. Okay, or if I wanted to write it as a combination of everything, this one will be anti-up up quark, anti-charm quark, or anti-up quark. Okay, so either one would do. Either you pick all of them being the same quark type, or you mix and match different quark types. Okay, as long as the fractional charge is -2/3e. Okay. Now, one thing I should probably mention here also is the term that you use for antiparticles. Let's just say, for example, when you're talking about the antiparticle equivalent of your up quarks, it is acceptable to write it as anti-up quark or up anti-quark. Okay, they mean the same thing, because sometimes when you look at the marking scheme and the textbooks, you may notice that the way they word the antiparticle equivalents as being different occasionally. Sometimes they say it's anti-up quark, sometimes they call it up anti-quark. They actually mean the same thing. Okay, you can write it any way you like. Even the marking scheme here is also saying that. You see, anti-up quark or up anti-quark, anti-charm quark or charm anti-quark, anti-top quark or top anti-quark. Okay, so that's it for this question. We're done with this paper.